I want to tell you about the most radical idea I've ever taken seriously. Not string theory, not the holographic principle, even though I helped develop it, not the multiverse, with its 10 to the power of 500 possible universes predicted by the string landscape. Those ideas are radical, yes, but they're radical in ways that feel like extensions of what we already know. More dimensions, more universes, bigger structures. Extrapolations outward from familiar physics. The idea I'm going to tell you about today is radical in a different direction, inward, downward, into the darkness beyond the horizon of a black hole. The idea is this: when matter collapses to form a black hole, it doesn't just compress, it doesn't just crush itself into a singularity and stop. Instead, the collapse continues through the singularity, through a quantum gravitational region we don't yet understand, and it bounces. It emerges on the other side as an expanding universe, a new cosmos, causally disconnected from ours, growing inside the black hole. Every black hole in our universe might be the seed of another universe, and our universe might itself have been born inside a black hole in some parent universe. Universes giving birth to universes, in an infinite chain of cosmic reproduction. I know how this sounds. It sounds like the kind of thing a physicist says when they've been working too hard and haven't slept enough. It sounds like science fiction. But it isn't. It emerges from serious, rigorous mathematics, from the general relativity equations that have been confirmed by every test we've run, from quantum mechanics, which has never failed an experimental test, from the combination of these two quantum gravity, where we're still working out the implications, but where the calculations point stubbornly in this direction. Let me show you why. Starting from the beginning, what happens inside a black hole. Let me remind you of what we actually know and don't know about black hole interiors. A black hole forms when enough mass concentrates in a small enough region. The escape velocity at the surface exceeds the speed of light. A boundary forms the event horizon inside which nothing can escape. Not matter, not radiation, not information. From outside, a black hole looks like a region of intense gravity. For observers far away, things falling toward the horizon appear to slow down due to gravitational time dilation, frozen at the horizon, never quite crossing. But this is an observational artifact. An infalling observer crosses the horizon smoothly, in finite proper time, without experiencing anything special. Inside the horizon, something dramatic changes. In the space-time geometry of the Schwarzschild solution, the simplest black hole solution, the time and space coordinates swap roles inside the horizon. What was the time direction becomes spatial, and what was the spatial direction toward the center becomes temporal. This has a devastating implication. Just as you cannot stop moving forward in time is mandatory, you can't stand still inside the black hole, you cannot stop moving toward the singularity. The singularity is not a place in space you could avoid by steering around it. It's in your future. It's where every time-like path leads. The singularity is where general relativity breaks down. The equations predict infinite space-time curvature, infinite density, infinite everything. But infinite predictions from a theory mean the theory has reached its limit of applicability, not that infinities actually occur in nature. Every physicist who has thought carefully about this believes the singularity is not real. It's a mathematical artifact of applying classical general relativity beyond its domain of validity. At Planck scale densities about 10 to the power of 94 kilograms per cubic meter, quantum gravitational effects must become important. The singularity prediction breaks down. Something else happens. The question is, what? The Penrose diagram and eternal black holes. To understand what might happen, I need to show you something called a Penrose diagram. These are extraordinary tools, conformal maps of spacetime, that compress infinite spacetime into a finite picture while preserving the causal structure. For an eternal black hole, one that has always existed and will always exist, a theoretical idealization, the Penrose diagram, has a remarkable structure. It's not just a black hole, it's two black holes, two universes, connected. The diagram looks like a diamond. The upper triangle is the black hole interior. The lower triangle is a white hole interior. The left exterior is one universe. Let's call it universe left. The right exterior is our universe, universe right. Universe left and universe right are connected through the geometry. They share the black hole's interior region, but, and this is crucial, they are causally disconnected from each other. No signal can travel from universe left to universe right, or vice versa. They share a geometry, a mathematical connection, but they cannot communicate. This connection between the two exterior regions is called an Einstein-Rosen bridge, or, in popular language, a wormhole. The first solution of this kind was found by Ludwig Flamm in 1916, 1 year after Einstein published General Relativity. Einstein and Rosen studied it carefully in 1935. For a long time, physicists regarded this as a mathematical curiosity. After all, no one creates eternal black holes. Real black holes form from collapsing stars. The full eternal structure, with its second exterior universe, is idealized. It doesn't apply to real astrophysical black holes. But maybe it does, in a quantum sense. Lee Smolin's cosmological natural selection. The physicist Lee Smolin, a serious, careful, creative theoretical physicist, proposed something audacious in the 1990s. He called it cosmological natural selection. Smolin's idea: when a black hole forms and matter falls toward the singularity, quantum gravitational effects cause a bounce. The collapsing matter doesn't just stop. It passes through what Smolin called a quantum bounce, a rapid, extremely dense phase, and then expands on the other side as a new universe. This new universe is inside the black hole from our perspective. It's causally disconnected from our universe. No signal can escape from inside the horizon. The new universe grows and expands independently. It's unreachable from our side. But it's a real universe with matter and energy, with space-time geometry, with physical laws. And here's Smolin's most provocative claim. The physical laws of the new universe are slightly different from ours. The fundamental constants, the strength of gravity, the mass of the electron, the cosmological constant are slightly different, with small random variations from the parent universe. This introduces something like evolution. Universes that have more black holes produce more offspring universes. The offspring universes inherit slightly varied parameters. Over cosmic generations, the parameters that produce more black holes will dominate the ensemble. This is natural selection, not of organisms, of universes. And Smolin argued that our universe's parameters, finely tuned as they seem, are not the result of pure chance, not the result of anthropic selection from a vast landscape, but the result of this cosmic evolution. Our universe is the descendant of many generations of universe formation and black hole production. Its parameters have been selected for black hole production. And perhaps coincidentally, perhaps not parameters that maximize black hole production seem to overlap with parameters that permit complexity, chemistry, and life. I find this idea beautiful. I'm not fully convinced by it. Smolin's argument has problems it's hard to formalize, hard to test, and the claim that small parameter changes always produce fewer black holes is not obviously true. But the core idea that black holes spawn universes, that there might be cosmic natural selection, this is a serious, interesting possibility that deserves attention. Quantum bounces and loop quantum cosmology. The most concrete theoretical framework for understanding what happens at the singularity comes from loop quantum cosmology. This is the cosmological application of loop quantum gravity, a competing approach to quantum gravity that takes seriously the idea that space-time itself is quantized. In loop quantum gravity, area and volume are quantized. They come in discrete units at the Planck scale. Space-time is granular, not smooth. It's a spin foam, a network of discrete quanta of geometry. When you apply this to collapsing matter, something remarkable happens. As matter collapses, it encounters a quantum gravitational regime where the discrete structure of space-time becomes important. The classical singularity is replaced by a region of extremely high but finite density. In this high-density quantum regime, the effective equations of motion include a quantum correction term. This correction term is repulsive. It creates an effective pressure that opposes further compression. And when the density reaches the Planck density, this quantum pressure exactly balances the gravitational collapse. The collapse stops, and then it reverses. The quantum bounce. After the bounce, the matter begins expanding again. But into where? In loop quantum cosmology applied to the Big Bang, the first successful application of this framework, the bounce, connects our expanding universe to a previous contracting universe. Before the Big Bang, there was a contracting universe. It bounced at Planck density and started expanding. That expansion is our Big Bang. Applied to black holes, the same logic suggests, after the bounce inside a black hole, matter starts expanding. This expanding matter forms a new universe, a baby universe, growing inside the black hole. The mathematics is consistent, the framework is well developed, if not universally accepted, and the conclusion is unavoidable. If loop quantum gravity is correct, black holes contain expanding universes. The information paradox connection. Here's where this gets deeply connected to the work I've spent my career on. As I've discussed many times before, in papers, books, lectures, and arguments that have spanned decades, black holes create a catastrophic puzzle for physics. The information paradox: when matter falls into a black hole, it carries information, the specific arrangement of particles, the quantum states of every atom, all encoded in the infalling matter. According to quantum mechanics, this information cannot be destroyed. The laws of quantum evolution are unitary. They preserve information absolutely. But Stephen Hawking showed that black holes radiate. They emit thermal radiation, Hawking radiation, that carries no information about what fell in. As the black hole evaporates, the information seems to be lost. This violates unitarity. It violates quantum mechanics. The resolution, I believe, in the one supported by AD's CFT correspondence, the holographic principle, and most of the quantum gravity community, after decades of debate, is that information is not lost. It escapes, encoded in subtle quantum correlations in the Hawking radiation. This requires the black hole interior to be somehow connected to the exterior in a way classical general relativity doesn't capture. But here's the tension with baby universes. If matter falls into a black hole and that matter seeds a new universe, if the information in the infalling matter is used to construct a new universe, then from the perspective of the original universe, that information is gone. It's in the baby universe. It's causally disconnected. From our universe's perspective, the information is lost, which violates quantum mechanics. This creates a genuine conflict between the baby universe picture and the information preservation picture. You can't fully have both. Either information escapes in Hawking radiation, no baby universe, or baby universe receives no information, or information goes into baby universes and is genuinely lost from our perspective. Most of us in the quantum gravity community believe information is preserved in Hawking radiation, which suggests that if baby universes exist, they must form in a way that doesn't capture the information stays in the original universe, encoded in the Hawking radiation. This is a live debate. It's not resolved, and it's one of the deepest questions in physics right now. The kerr, black hole, and hidden universes. Now let me tell you about something more specific and more mathematically well established. The interior of rotating black holes. Most real astrophysical black holes rotate. Angular momentum is conserved, and when massive stars collapse, they collapse with significant rotation. These are called kerr black holes, after Roy Kerr, who found the solution in 1963. The interior structure of a kerr black hole is dramatically different from a Schwarzschild black hole. Instead of a point singularity, there's a ring singularity, and the Penrose diagram for a kerr black hole is mind-bending. Inside the outer horizon of a kerr black hole, there's another horizon, the inner Cauchy horizon. Inside the inner horizon, the character of space-time changes again. The singularity is off to the side. You don't have to hit it. You can potentially avoid it. And the Penrose diagram extends infinitely beyond the ring singularity, through the inner horizon, and back out through the outer horizon. You emerge into a completely different exterior space-time region, a different universe. And the diagram continues. Another universe and another in an infinite tower of connected space-time regions. Now, the physical relevance of these extended kerr solutions is debated. They're solutions of the classical equations, whether they survive quantum corrections, whether the inner Cauchy horizon is stable when quantum effects are included, whether the infinite tower of universes is real. These are open questions. Most physicists suspect that the inner Cauchy horizon is actually violently unstable. Small perturbations are infinitely blue-shifted as they approach it, creating an effectively infinite energy density that destroys the horizon structure. The idealized mathematical solution is probably not physically realized. But probably not realized in classical general relativity is different from not realized when quantum gravity is taken into account. When we properly quantize the geometry of the kerr interior, which we haven't fully done, the inner horizon might be stabilized, the singularity might be resolved, and those other space-time regions might be real. We don't know. And that uncertainty is exciting. The Wheeler-DeWitt equation and quantum cosmology. Let me go deeper into the mathematics of quantum gravity and what it says about the birth of universes. In the 1960s, John Archibald Wheeler and Bryce DeWitt wrote down an equation that was supposed to be the quantum gravitational analog of the Schrödinger equation, the fundamental equation governing quantum states of geometry. It's called the Wheeler-DeWitt equation. The equation is psi equals 0, where I is the Hamiltonian constraint of general relativity, and xi is the wave function of the universe, the quantum state of all geometry everywhere. The Wheeler-DeWitt equation is notoriously difficult. It's technically problematic. In many ways, it's not entirely well defined as written. It has issues with time. What does time mean in a theory of quantum gravity where time is part of the geometry? And solving it for realistic cases is beyond our current capabilities. But it has been studied in simplified cosmological settings. And what it describes is a wave function that assigns amplitudes to different three-dimensional geometries, different configurations of space. In this quantum cosmological picture, a universe isn't a definite space-time. It's a quantum superposition of different geometries, different sizes, different shapes, different topologies. And crucially, the wave function doesn't require that the universe have a beginning. The Hartle-Hawking no-boundary proposal, developed by Jim Hartle and Stephen Hawking, gives a specific wave function for the universe that describes it as emerging from a quantum fluctuation. No singularity, no before the Big Bang. The universe simply quantum mechanically comes into being. In this framework, there's no reason why the quantum cosmological wave function should be restricted to a single universe. The wave function can have amplitude for multiple disconnected universe components, for topological handles connecting different regions, for baby universes budding off from parent universes. Wheeler was obsessed with this. He talked about quantum foam, the idea that at the Planck scale, space-time topology itself fluctuates, wormholes appear and disappear, baby universes bubble off and reconnect. The fabric of space-time is not smooth but seething with topological activity. If Wheeler was right, baby universes are not exotic speculations. They're intrinsic to quantum gravity, the cosmic censorship and naked singularities. There's a related question that bears on all of this: cosmic censorship. Roger Penrose proposed the cosmic censorship conjecture in 1969. Naked singularities, singularities not hidden behind event horizons, cannot form in physically realistic situations. Every singularity is clothed in a horizon. If cosmic censorship holds, then every singularity that forms in our universe is inside a black hole. Every singularity is hidden from us, and if singularities are replaced by quantum bounces that produce expanding universes, then every black hole in our universe contains a hidden, growing universe. Our universe has billions of galaxies, each with a central supermassive black hole, plus stellar mass black holes throughout, plus primordial black holes that might have formed in the early universe. The total number of black holes in the observable universe is estimated at perhaps 10 to the power of 18 billion. If each one contains a universe, then our universe is pregnant with a billion universes. Each potentially containing its own black holes, each of those containing universes, in an infinite recursive structure. The sheer scale of this is vertiginous. The multiverse from the string landscape involves a vast but perhaps finite number of different universes with different physical laws. But the baby universe picture, if it's correct, involves literally infinite universes nested inside each other, an infinite fractal of cosmoses, and all of them are happening right now. Every black hole forming right now in stellar collapses, in neutron star mergers, in the centers of active galaxies, is potentially spawning a new universe as you watch this. Observational implications. Let me ask the hard question: is any of this testable? Honestly, direct observation of a baby universe is impossible, by definition. A baby universe is causally disconnected from ours. No signal can escape from inside a black hole. If a new universe is growing inside a black hole, we can never observe it directly. But that doesn't mean the baby universe hypothesis has no observational consequences. If Smolin's cosmological natural selection is correct, it makes predictions about the values of physical constants in our universe. Specifically, our constants should be near optimal for producing black holes. If we could show that small changes in any constant would produce significantly more or fewer black holes, that would be evidence for the selection hypothesis. This prediction has been studied. Results are mixed. Some constants do seem to be near black hole production optimal values. Others don't obviously satisfy this. The analysis is difficult because simulating alternative universes with different constants is hard. More concretely, quantum gravity phenomenology. Effects of quantum gravity on the black hole interior might leave signatures in the Hawking radiation that is emitted. If the quantum bounce inside a black hole affects the quantum state of the infalling matter in specific ways, those effects might be encoded in correlations in the Hawking radiation, which, in principle, contains information about the black hole interior. We cannot currently measure Hawking radiation from astrophysical black holes. The temperature is far too low. But gravitational wave observations of black hole mergers are revealing the dynamics of black hole formation and merger in detail. As detector sensitivity improves, these observations might constrain quantum gravity effects that are relevant to what happens near singularities. And there's the cosmic microwave background. If our universe was itself born from a bounce inside a black hole in some parent universe, that birth process might have left signatures, statistical anisotropies, non-Gaussianities, specific patterns in the primordial power spectrum that we could detect in precise CMB measurements. The CMB, S4 experiment, and future space-based CMB missions will probe the primordial universe with extraordinary precision. If our birth left marks, we might find them. The philosophical depth. Let me step back from the technical details and ask, what does it actually mean for a black hole to contain a universe? First, the word contain is misleading. We say the new universe is inside the black hole, but inside and outside are spatial concepts, and what we're really talking about is causal structure, not spatial nesting. The baby universe is in the causal future of the collapsing matter. From our universe's perspective, that causal future region is inside the horizon, inaccessible. From the baby universe's perspective, it's a new, expanding cosmos with no horizon. It doesn't feel like it's inside anything. This is deeply analogous to a question about our own universe. Are we inside a black hole in some parent universe? From our perspective, we're in a normal universe. There's no horizon around us, no sense of confinement. But from the parent universe's perspective, if it exists, we might be a region inside a horizon, causally disconnected. We would never know. The physics inside would look the same whether we're in a parent universe's black hole or not. Our universe could be a black hole interior, and we would have no way to detect it. Second, the new universe is genuinely new. It's not just a region of our universe. It's topologically disconnected. It started from a quantum bounce with its own initial conditions. It might have its own values of fundamental constants. It will evolve independently for all of cosmological time without any connection to our universe. Third, there's no center. The baby universe doesn't exist at a spatial location inside the black hole from our perspective. The black hole looks like a region in our space. But the interior is a separate space-time. It's not located anywhere in our space in the ordinary sense. It exists in its own space-time with its own spatial coordinates. This is one of the hardest things to internalize about black hole interiors. The interior is not a place in our universe that we could, in principle, travel to if we could just get past the horizon. Well, we could travel there by falling in, but once inside, we'd be in a space-time region that has no spatial connection to our universe. We can't send messages back. We've genuinely left the self-reproducing universe in consciousness. Here's where I'm going to venture into territory that makes me uncomfortable, but that I think deserves honest examination. If universes reproduce through black holes, and if the production of consciousness-bearing creatures is related to the production of black holes because both require stars, which form from the same conditions that produce black holes, then cosmological natural selection might explain the existence of conscious observers. Not through anthropic reasoning, not through the fine-tuning argument, through actual natural selection pressure on universal parameters. Universes that produce more black holes tend also to produce more complexity, more chemistry, more biology. Over cosmic generations of universe reproduction, these properties become common. And conscious observers find themselves in universes with these properties, not because those are the only universes compatible with consciousness, but because those are the most reproductively successful universes. I want to be careful here. This is speculative, very speculative. I'm not claiming it's correct. The connection between black hole production and consciousness is not rigorous. Smolin's cosmological natural selection is an interesting hypothesis, not an established theory. But it's genuinely different from both the traditional anthropic principle and traditional fine-tuning arguments. It gives you a mechanism for why physical constants have their values. A mechanism that doesn't invoke observers. A mechanism that works through cosmic scale natural selection operating over infinite time. If true, it would mean that life and consciousness are not accidents, not miraculous improbabilities, not anthropically selected flukes. They're the natural result of a cosmic evolutionary process selected for indirectly by the same laws that create black holes. My own position. You deserve to know what I actually think about all of this. I am genuinely uncertain. I believe the singularity is not real, that quantum gravity resolves it. This is not controversial among theoretical physicists. We all believe this. I believe that what replaces the singularity involves quantum gravitational effects that are not yet fully understood. Also not controversial. Whether those effects produce a quantum bounce, a baby universe, a new cosmos, this I don't know. The loop quantum gravity calculations suggest a bounce. The ADS CFT calculations suggest something more like the information being scrambled and re-emitted in Hawking radiation. These two pictures are in tension. I spent years fighting for information preservation against Hawking. I believe strongly that information is not lost in black holes, that quantum mechanics is preserved. And this belief creates tension with the baby universe picture, as I explained earlier. But I've also learned in 50 years of physics that my intuitions are not always right, that the universe doesn't care what I find convenient or philosophically satisfying, that the mathematics sometimes leads to conclusions I didn't expect and didn't want. If the loop quantum gravity community is right, if their calculations of the quantum bounce are robust, then baby universes are real, and we need to grapple with what that means for information, for quantum mechanics, for the whole framework. If the holographic community is right, if information is preserved in Hawking radiation and the interior is fully reconstructible from the exterior, then maybe baby universes don't form in the way Smolin describes. Or maybe they form but without capturing information. The mathematics might be compatible after all. We don't know. And that's the honest answer. The most exciting answer in physics is always the same. We don't know, but here are the possibilities, and here's what we're doing to find out. What black holes have taught me. Let me close by telling you what thinking about black holes for 50 years has actually taught me. Black holes are not just strange astrophysical objects. They're windows into the deepest structure of physics. Every time I think I understand a black hole, it reveals something new about the relationship between gravity, quantum mechanics, information, and space-time. The Hawking radiation calculation showed me that quantum mechanics and general relativity, naively combined, give nonsensical results. Information can't be lost, but it seemed to be lost. This paradox drove 30 years of research and led to the holographic principle, ADS CFT, and a completely new understanding of how space-time can emerge from quantum information. The baby universe possibility shows me that even the topology of space-time, the connectedness structure of the universe, might not be fixed. Space-time might be able to branch, to reproduce, to create new connected components. The universe we inhabit might be one branch of an infinite fractal of spacetimes. The singularity problem shows me that general relativity is incomplete, that spacetime, in extreme conditions, becomes something we don't yet understand. That quantum gravity, the unification of quantum mechanics and spacetime, is not just a technical problem, but a conceptual revolution waiting to happen. And the information paradox, after decades of struggle, shows me that the deepest truths in physics come from taking contradictions seriously. When two well-established principles contradict each other, the resolution doesn't come from abandoning one of them. It comes from discovering a deeper principle that contains both as special cases. Black holes might contain universes, or they might be the most efficient processors of quantum information in existence, or they might be both in ways we haven't figured out yet. Or they might be something else entirely, something we haven't thought of. that future physicists will discover by staring at the equations longer and harder than we have. The equations are there, the mathematics is clear. As far as it goes, what we lack is not intelligence or effort, but the right conceptual framework. And that, I am certain, will come. Maybe not in my lifetime, but it will come. Because the universe is comprehensible, and physicists are stubborn, and the black hole at the center of the Milky Way is sitting there, 30,000 light years away, waiting patiently for us to figure it out. Conclusion. Let me tell you what I know, what I suspect, and what I don't know. I know black holes are real, singularities form, general relativity predicts infinite curvature there, but that prediction is wrong. It signals the breakdown of the theory. I know. Something happens at the singularity that we cannot currently describe. Quantum gravity is required. We don't have a complete theory of quantum gravity. I suspect. The singularity is replaced by a quantum bounce. Collapsing matter reaches Planck density, encounters quantum gravitational repulsion, and bounces. The bouncing matter begins expanding. This expansion looks, from the inside, like a big bang. I suspect the new expanding region is causally disconnected from our universe. It is in all meaningful senses a new universe. I don't know whether this baby universe captures information from the parent universe or whether information is somehow preserved in our universe's Hawking radiation. This tension is unresolved. I don't know whether the constants of physics in the baby universe are the same as ours, or different, or randomly varied, whether Smolin's cosmological natural selection is correct. I don't know. Whether our own universe was born from a bounce inside a black hole in some parent universe, we would not be able to tell. The physics inside looks the same either way. What I believe, in the deepest sense, is this. The black hole is not the end of the story. Matter does not simply fall in and vanish. Spacetime does not simply terminate at the singularity. The universe is richer, more connected, more alive than the classical picture suggests. And somewhere, right now, in the heart of every black hole in the observable universe, something extraordinary might be happening. A quantum bounce, an explosion of new spacetime, a cosmos being born in darkness, growing in silence, utterly disconnected from us, other universes. Happening right now, inside black holes we can see with our telescopes. If that isn't worth thinking about for 50 years, I don't know what is.